Here are the highlights concerning projectile motion. Projectile motion means that the x and the y directions of motion act independently, and that's going to be true in every case. The velocity in the x direction doesn't change since there's no force acting on a projectile. The velocity in the y direction does change. It accelerates at the rate of negative 9.8 meters per second squared because it feels that downward force. What links the x and y directions is time, and so it's oftentimes useful to find at the beginning of a problem. I call it flight time, so how long is the projectile actually in the air? You're going to want to use our kinematics equations in the x and y directions. One of the things I really dislike about our textbook is they give you a million equations and they list the x and the y. You're not going to get those on your tests. What we need to do is we need to use our three base equations. And when we use our base equations, we can use them in any context, and we need to know how to do that. So I'm always going to refer you back to these three basic equations. The top one I call the position equation because it tells how position changes over time. Next one is velocity. And then lastly, we're using that velocity equation that has no time in it. So that's oftentimes useful if you don't have time. I want to reiterate that these equations are only used when we have situations with constant acceleration. And in this case, we do because we have a constant acceleration of that negative 9.8 meters per second squared in free fall. The other thing that I want you to note about these equations is that they can be used in both the x and the y direction. So in this format, they're written in the x direction. We can just change subscripts and put them in the y direction and use them in the same way. Now, they are going to take a little different format. So for instance, in the x direction, there isn't going to be acceleration. So we would not use that term of the equation. Also, this one wouldn't be valid in the x direction, but it definitely is valid in the y direction in projectile motion. Okay, so this picture up here is an interesting picture. It is like a time-lapse photo. It's taken in multiple millisecond iterations, and the red ball is a ball that's simply released, and then this yellow ball is projected outward. And what's interesting to notice is that each instant in time, as that ball is falling, they're at the same vertical height. However, that motion of that yellow projectile does move in the x direction, but this picture shows the independence of the x and the y direction. Because even though the yellow ball is projected in the x direction, the y direction of both of them are equivalent as time progresses. We're going to be doing example number 32 on page 79. And at this time, I need you to open up your book and I need you to draw a picture of what this situation looks like. Here is my picture. I didn't have a nice image of Kyle serving this tennis ball, otherwise I would have put that in there. But this is the image that I have. So we have the 12 meters to the net, the 0.9 meters to the height of the net, 2.7 meters where that ball is launched, and then that initial velocity in 23.6 meters per second. The next step in solving a projectile motion problem is listing your variables. And I'm going to ask you to make two lists, an X list and a Y list. Remember when I said how projectile motion is the X and Y act independently? This separate list of X and Y is really going to help. So I'll give you an example of what I mean. What I want you to do is I want you to make a list in both the X and the Y directions. So notice I have initial velocities, initial positions, final positions, and acceleration. So I did that for your X direction. I'd like you to try that for your Y direction. Model it after what I've done. So I've listed my variables here. I asked you to do the x direction, or I gave you the x direction. I asked you to do the y direction. So the initial velocity in the y direction was 0, since this is launched in a horizontal direction. The initial position in the y direction is the 2.73 meters. The final position of the y is unknown. So the question asks, does the ball clear the net? So essentially what we want to know is, what is the y position when it reaches the net? So what we want to do is we want to figure out what that y position is, which is why I left it a question mark. The other important thing we need to know is that the acceleration in the y direction is going to be negative 9.8 meters per second squared. So the fact that the x and y act independently is really important. The thing that links those two together is the time, or the time of flight. And in this case, we can find the time of flight first. And oftentimes in projectile motion, that would be my first suggestion for you. So what we're going to do now is we are going to use the time we're going to find the time of flight, and we actually need to do that in the x direction. A lot of times we use the y direction to find times of flight because the y direction actually dictates the time of flight. If you think about it, the acceleration is what pulls that ball back down to the ground. And so the y direction oftentimes dictates what the flight time of our object. But in this case, we don't know what our final y direction is. We don't know if it hits the net. We don't exactly know. But we do have quite a bit of information in the x direction. If you just look at the variable column in the x direction, look how many things we know about the x direction. And so oftentimes, the more you know about one of the two directions, that's the direction you want to start working in. So with that being said, we need to go back to our kinematics equations, and we need to choose one of our kinematics equations to use to find the flight time. And we know that our velocity in the x direction doesn't change over time. And so this equation, that second equation, is not really going to be very useful, nor will that third equation. We're actually going to use our position equation. And I'm going to ask you to go ahead and use the position equation to find the flight time. So right now, I want you to use the position equation to find the flight time. Using the position equation in the x direction, I realized that in the x direction, I have no acceleration, right? And so we are going to substitute in our initial velocity in the x direction, which I should note that the initial velocity in the x direction actually stays the same. That 23.6 meters per second in the x direction stays the same as it flies. And substituting in our 12 meters for our initial position, our final position, that's the position at the net, our initial position of 0, and we solve that down. So this would be 12, this would be 0, our initial velocity, and then solve for our time. That will give us our time of flight to 0.508 seconds. So if we think about that path or the trajectory that you learned about doing that PhET simulation, this tennis ball is going to do something like this. And what we want to know is, does it clear the net? So does it land down here, or does it land up here at that 12 meters, which is why we put the 12 meters in our position equation. Okay, so our next step then is to find that y position at the location of the net. So we know how long it takes the ball to get to the net, 0.508 seconds, but what we need to do is we need to find where that object is up and down. Now listen to the word that I use. I just said where. Isn't that a position, right? A position of where is the object in the y direction after it has been in flight for 0.508 seconds. So our next step is to go back and look at our equations. And I am going to, again, erase some of this because we actually are going to need some of these. We're looking for a location, right? So we're looking for a location. So thinking about the list of equations that we have, this equation does not give us a location, right? It just gives us information about velocities. Now, this one would give us some information about locations, but we don't know how fast this object is traveling in the y direction when it reaches the net. This equation is going to be the one that we want to use. So we're going to choose this equation, but we're going to rewrite it in the y direction. So what I mean y direction, it's going to look like this. Y is equal to y naught plus vy naught t plus 1/2 at squared. And technically that acceleration would also be in the y direction. So we're going to use that position equation to solve for the location of the ball at the time that it is reaching the net. So see how that time links those two directions, the x and the y direction. So what I want you to do is I want you to use your position equation in the y direction, use your list of variables, substitute in solving for the y position at the net, which occurs at the time of 0.508 seconds. So again, pause the video, solve for your y position. So I use my position equation in the y direction, and I want to find again where the object is or where the tennis ball is when it reaches the x direction of the net. The initial y direction or the initial y position is at 2.37 meters. And then this term here is 0 since the initial velocity in the y direction is 0. And I know that because this ball is launched horizontally. It's not launched up or down, and so we have an initial y direction of 0. We substitute in our acceleration. Notice that's negative. That's important. And our time. I am carrying an extra digit in my intermediary calculations of time just so that we have a little bit more accuracy. And the position of the ball is 1.1 meters above the ground. And so it does clear the net since the net is 0.9 meters high. And so the difference between the height of the net and where the ball is about, 0.2 meters. All right, so we have now finished part A and part C. Now what I want to do is I want to start looking at we finished A and B, excuse me. We need to start looking at part C. So part C now says, suppose that instead the ball is served as before, but now it leaves the racket at 5 degrees below the horizontal. Again, when the ball reaches the net, does the ball clear it? And what happens? So what I'm going to have us do right now is the same kind of idea is we're going to redraw a picture. We're going to relist our variables, and we are going to start solving this. So I'm going to give you all a nudge. I'm going to give you a start, and then I'm going to have you go from there. So if we think about how this is going to look, I'm going to make this a little bit bigger so we can see. Instead of having our initial velocity be directly to the left, we have an initial velocity that is still the 23.6 meters per second, but this time it's at a downward angle of 5 degrees. And so we're going to have a different velocity initial in the x direction and in the y direction. So I've blown up this vector over here, this 23.6 meters per second, so that we can draw its x and its y components. All right, so I'm going to give you all a little bit of rain and a little bit of freedom, but you're going to repeat the process that you did before, but this time you are going to have different initial velocities. So let me give you a couple more pieces of information and then turn you loose. So here is our 5 degrees. We have an initial velocity still of 23.6 degrees meters per second, 23.6 meters per second. You want to find your initial velocity in the x direction and your initial velocity in the y direction. So you want to find those two components of that vector. You're going to list those here and here. And then you're going to go through the same process in finding your flight time as well as your vertical height. So I'm going to have you almost like wrap this problem up. So I'm going to let you think on your own. You need to, again, find your X and Y components of your initial velocity. You need to find your flight time, and then you need to find that vertical position when the ball reaches the net. You've probably noticed as I have made this video that the sun has been going down, and so it continues to get darker and darker in here, and I don't have a light in the ceiling, so I'm sorry if you can't see me very well, but you should be able to see the screen. So I found my components of my velocity in the X and the Y direction. So that X direction initial velocity, which again stays the same over time, is at 23.51 meters per second. And then that Y velocity, and I should note that that Y velocity is actually negative. So let's take a moment and note that that Y velocity is indeed negative, and it's negative because that velocity has a downward component. When you substitute in your velocities in your X direction in order to find the flight time I found was about 0.510 seconds, which is pretty close to the flight time that we saw when that ball was launched horizontally. We're going to use that new flight time and put that in our Y direction position equation. Now I want you to notice how very different that final Y position is. Two things, if you didn't get that answer, check to make sure that the velocity in the Y direction is negative, right? Because that is downward, and again, that makes a difference. So that clearly does not clear the net. So that ball is gonna like right there and hit the net, and that serve will not go over. And I think maybe Kyle can attest to this. Tennis is a super hard sport. A difference of 5 degrees means the difference between clearing the net by 20 centimeters or not clearing the net at all. So to summarize the big ideas in projectile motion, what you need to remember is you need to draw your picture, draw your picture, draw your picture. Make a list of your X and your Y variables separately. Find flight time. That's helpful in linking the two together. Use your kinematics equations in their simplest forms in both the X and the Y direction, remembering that the X direction velocity stays the same over time. Good luck in solving those projectile motion problems.